Okay, welcome back everyone. I'm back from a fairly complicated grant administration round, and so we can now continue these lectures. Now, as you hopefully remember from about a month ago, we ended with defining Lie groups and Lie algebras and their various interrelations, and stopped shortly after we considered SU2 group and the SU2 Lie algebra. And we considered them because they happen to describe a spin-half particle. We then proceeded to look at the spatial rotations. The SO3 group looked at its irreducible representations and constructed some practical recipes for rotating spin systems in 3 dimensions, which, as you'll see hopefully when you do your own simulations, are very handy when you do relaxation theory and things like boundary averaging. But what we'll do today is continue with the quantum mechanics part of it and look at the SU groups in some more detail. And in particular, we shall look at SU2 and its relationship with SO3, and also SU3 as a brief insight into how these things can be generalized with a little bit of hand-waving introduction to how particles are classified in particle physics. But okay, so we go into SU2 today, and this touches upon the historical matter of considerable interest, that is, on how spin actually came to be discovered. Now, as you hopefully remember from your undergraduate course, the turning point was the observation by Stern and Groach that in magnetic fields, when you pass a beam of ions through it, the beam splits into 2. It clearly interacts with the magnetic field, and it clearly interacts with it in a way that has 2 observable states. And from our general knowledge of quantum mechanics and a bit of philosophy around it, we know that the observable states, well-defined states, correspond to eigenfunctions and the corresponding parameters that we observe to the eigenvalue, if it's an individual particle. And those definitely were. So we had, or rather the community had at that point, a pretty interesting dilemma. Now, imagine that we are trying to build a theory of whatever it was. And in quantum mechanical formalism, there would be an operator. Let's call it a spin operator. We absolutely do not know what it is. And in Schrödinger's picture, it would have been a differential operator. Yeah, it would be some functional something in here, containing maybe derivatives, maybe something else, but it would be an operator that would act on a space of wave functions and return some other wave functions or transform it somehow. Now, you see the primary difficulty with this thing. Any differential operator would have necessarily an infinite number of eigenfunctions, because it acts on the Schrödinger function space, the Hilbert space, which has infinitely many functions in the basis, and it would then have to transform them and get infinite number of other functions. You can diagonalize it, get an infinite number of eigenfunctions. So it's not possible in the Schrödinger picture to actually find an operator that has exactly 2 eigenfunctions. In the wave function picture, it is not possible. Now, of course, it is possible in the Heisenberg picture, where we can simply put up a 2 by 2 matrix and say that, well, okay, there are some internal states and this is the matrix that acts on them, that's the Hamiltonian. But of course, the great sacrifice that would have to be made is the breaking down of the beautiful correspondence between the Schrödinger and the Heisenberg picture. Well, various other possibilities can be considered, and one of them was to try and treat spin as an intrinsic angular momentum. Of course, this faced several problems almost immediately, as understood at the time in 1930s. Electron was a point particle and could not, as a point particle, actually rotate or have an angular momentum because there is no tensor of inertia. So that was difficulty number 1. And difficulty number 2 is that, as you remember, the angular momentum was obeying SO3. And the SO3 group and the associated algebra only have odd dimensional irreducible representations. We could have momentum equals 0, momentum equals 1, momentum equals 2, and so on in the quantum numbers. And the reason why it was discretized was pretty fundamental. It was the 2 pi periodicity of the rotation. So this was a 1-dimensional irrep, this was a 3-dimensional irrep, this was a 5-dimensional irrep. There is nothing here with 2 dimensions. Now, if we were to try and force some kind of formalism that would have even-dimensional irreps, then within SO3 what would happen is the resulting physical space would have a very bizarre interpretation. It would mean that upon the full rotation by 360 something changes sign. Now, clearly a nonsensical proposition here in the physical space. And to that effect I have included a letter by L.H. Thomas to Sam Goodsmith, one of the co-authors of the original paper on spin from 1926, which you can read to your enjoyment. And it's ironic that Pauli was so critical about it. Well, you can see why he would be so critical, because almost anything you try ends up in something that's fairly unpalatable, based on the angular momentum theory and the general quantum mechanics that was known at the time. But as soon as he came to terms with it, he in fact proposed the fundamental representations, the Pauli matrices, and then made a seminal contribution to the theory of spin. So what we'll now do is just follow Pauli and build the theory of spin from scratch. Now, I should warn you here, and I think I've said it previously, that the analogy with the classical angular momentum, the angular momentum corresponding to rotation, is deeply misleading. That is, even though SU2 and SO3, as we'll see, share some similarities, they are very fundamentally different. SO3 is about rotations in this physical space. You take a chair and you rotate it. SU2 of spin is about taking linear combinations of wave functions in a 2-dimensional wave function basis, in a space of internal degrees of freedom of a particular particle, which needn't correspond to any particular things in this 3-dimensional reality. So even though the corresponding Lie algebras, as we'll see, are actually isomorphous, from the physical perspective, SO3 of rotation and SU2 of spin have absolutely nothing in common. This confuses philosophers a great deal, who start talking about 4 pi periodicity in real physical space. As you can probably tell by now, it's a simple fallacy. Right, so what Pauli did is suggested a simple, or well, perhaps a desperate thing. He said, okay, we had these functions, psi, x, y, z, and they were living in our nice C3. So they were inhabiting, well, it would take R3 and map it into a complex number, and the dimension of the space of wave functions is infinite. And so what Pauli did was to say, well, okay, we have this C infinity, the space of all complex functions, and let's just cross it with a C2. So what we'll do is we'll take C infinity, where the wave functions live, and we'll just double it. We'll cross with it a 2-dimensional vector space. And then ask ourselves, what are the most general kinds of transformations that preserve the norm and are continuous on C2? Now, if it has to preserve the norm, then it necessarily has to be some kind of unitary group. If it has to be continuous, so there has to be a continuous path between every 2 operations in the group, it has to be special, SU. And if it's a 2-dimensional vector space we are transforming, then it will be SU2. Now, you see, we haven't actually derived this from anywhere, or arrived at it from anywhere. We simply asked, based on what we know about quantum mechanics, that any transformation has to preserve the wave function norm, because those are probabilities, and that it has to be continuous, nature, if you look at it very closely, almost anywhere would be a continuous thing. Then what is the most general possible group of such transformations? And the group turns out to be SU2. And then things that live here came to be known as spinors. If the particle has greater number of internal levels, energy levels, or internal degrees of freedom, or however you put it, then 2, then well, we can cross it with C3, C4, and so on, and the corresponding groups in here would be SU3 and SU4, and so on. These are the most general possible cases. And then, of course, in general, it will be cross C2J plus 1, where J is the spin, and you can see how the historical analogy with quantum mechanical description of angular momentum muddies the water here. This came from angular momentum, whereas necessarily, well, it needn't necessarily be the case for spin. It will just have every possible dimension of the irreducible representation. Right, so what we then have is these SUN groups of unitary transformations, and of course there are corresponding algebras. If we take a tangent space transformation, we get them reciprocally. An exponential map takes us there, so SU2 and so on, the algebra, and we'll be dealing chiefly today with these algebras. Now there is another matter which I have to touch upon. You can see things like SU3, SU4 and so on made an appearance. This might surprise some of you who did particle physics before, because those who did particle physics know that spin is in fact classified according to the irreducible representations of SU2. Now, very importantly, this is not the case in magnetic resonance. Now, the reason for that is, in the case of SU2, we had the two-dimensional irrep, the fundamental irrep, which corresponded to spin half. Then we had a three-dimensional irrep corresponding to spin 1, and so on. They all had their Lx, Ly, and Lz operators, which are the generators of SU2, and they could have any dimensions, 1, 2, 3, 4, corresponding to different things. Now, that is only the case in particle physics, because spin of a particle is considered to be strictly SU2 symmetric. That is, the spacings between energy levels, let's say for a spin 1, between the top two energy levels and the bottom two energy levels are exactly the same. So let's say isolated spin in vacuum. In magnetic resonance, however, we know that there are various effective couplings, like quadrupolar coupling, which is actually electrostatic, but manifests itself as spin coupling, that do actually change those energies. And in the case of a spin 1, in vacuum, what we would have is 3 levels for spin 1 with exactly equal separation in here, and these two transitions cannot be addressed independently, and it can be shown that the resulting symmetry is SU2. In a magnetic resonance system, where the particle happens to have various interactions, such as quadrupolar interaction, what would happen is the interactions would actually change these energies, and under a quadrupolar interaction, let's say we've got this picture, this energy becomes different from that energy. The two transitions can be addressed independently, and then the system behaves as a general 3-level system with 3 wave functions here. And for a general 3-level system, described by a 3-dimensional state vector, the group of unitary transformations is SU3. So the particle physics books are correct in that spin is classified by the irreducible representations of SU2. However, then the multiple interactions that we have in spin dynamics introduce corrections to that, and spin J actually behaves dynamically and evolves under the action of the full SU2J plus 1. It will take a while to get used to, but let's just say that in the most general possible quantum mechanical context, if we have a spin J, its dynamical group is SU2J plus 1. Right. Well, this can actually be demonstrated quite easily for quadrupolar nuclei. If we take spin 1, then things like Lx, Ly, and Lz will definitely span SU2 and generate SU2 group. However, if we add to these the quadrupolar interaction operators, what we will also have is Lz squared minus a third E, I think it's a third, yeah, 2/3 E. Then Lx squared, Ly squared, Lx y, and Lx Lz. 1, 2, 3, 4, 5, 6, 7, 8. How many generators does SO3 have? SU3 have? 8. And these are in fact related to the Gell-Mann matrices, as we'll see in a moment. So the presence of extra interactions in quadrupolar resonance means that in this case, in presence of those interactions, spin 1 is actually described by SU3. Right. In order to proceed with classification of various irreps, we need to make a few more definitions. In particular, before we move on to the roots and weights of these algebras, we need to define what is root and what is weight. Again, I have to apologize to the physicists present who have had a gory amount of particle physics in their second and third year, but for the benefit of the chemists present, we do have to actually go through all of that. Right, so if G is a semi-simple Lie algebra, semi-simple, for what it is, look at the previous lectures, and H is a subalgebra of G, and also is an abelian subalgebra. So all elements of H commute between themselves. Then, if H is also the biggest such subalgebra, so maximal, then H is called a Cartan subalgebra. That is the definition of a Cartan subalgebra. Now, if we have those elements, H1, H2, and so on, Hk, mutually commuting, then the algebra H is spanned by these operators, H2 and so on, Hk. To make it a basis set, we'll demand their orthogonal. And the definition of a weight is the eigenvalue of these H1, H2, and Hk of a specific number. So we'll diagonalize them. And then a weight, mu, let's say J of Hk, is the jth eigenvalue of Hk. And you can see it's a vector. That is, if we take j's eigenvalue of H1, H2, and so on, Hk, we'll have a vector with k elements. So in the general case, it is a vector, but as we'll see in the simple case of SU2, it's actually a scalar because there is only just one element in the Cartan subalgebra, the Lz, because it's not possible to find anything else that actually commutes with it except itself. So the weight is defined somewhat obscurely for the time being as the j's eigenvalue of the kth basis operator of the Cartan subalgebra that has been diagonalized. Right? So, well, what we can observe immediately is that weight is a linear function on that algebra if we take mu j and we take linear combinational operators A alpha plus beta b. Then this will be alpha mu j A plus beta mu operation. And then vectors of this form, so if we take a particular j's eigenvalue of each of these matrices and write it out into a vector, so it will be mu j of h1, then mu j of h2, and so on, mu j of hk. That's called a weight vector. Okay, so let us now make this slightly more understandable, I guess, by looking at the specific examples. And I'll be using SU2 and SO3 as a test case. And at least in the case of SU2, you will instantly recognize these things because we've been through them many, many times. First for angular momentum and then for spin. It's a bit more complicated in the case of SU3, but thankfully we don't actually have to go that far in this course. Really, by the time you are hitting something that's more complex than just a single spin, it's time to fire up some numerical simulation package. And in that case, you don't have to worry about actually writing out all these huge matrices one by one. Okay, so let's take a look at the weights of a couple of algebras. In the case of SU2, the Cartan subalgebra is just generated by LZ. Because LZ is 0. There are two other Cartan subalgebras, of course. LX is 0 and LY is 0, but we just have to pick one of them. And because nothing else can use with LZ in that algebra, we just have a one-dimensional Cartan subalgebra there. So, okay, let us diagonalize LZ. Well, we know which diagonal already. It's the LZ Pauli matrix. It's got a half and minus a half on the diagonal. And now take the basis vectors of that space, namely 1, 0, 0, 1, and take a look at the corresponding eigenvalues. So the weight in this case is not a vector, it's a scalar because we only got one operator in this Cartan subalgebra. It's a number, and well, we know very well what that is. LZ S mu is mu S mu. Here, the usual spin eigenfunctions and the corresponding eigenvalue, and that is plus minus a half. So these are the weights of SU2. Well, they do of course depend on the representation. If we take spin greater than a half, so let's say S equals 1, LZ 1 mu is mu 1 mu, where this will be minus 1, 1, 0. So the three-dimensional irreducible representation has got 3 possible values for the weights, whereas this one only has 2. And we can build what's known as the weight diagram. So if we draw an axis here, that's the LZ. For spin half, we will have 2 weights, a half minus a half. For spin 1, we will have 3 weights, denoted with crosses. So minus 1, 0, and 1, and so on. And the transition between these weights is accomplished by the raising and lowering operators. So transition up is L plus, and transition down is L minus. Okay, now let's take a look at something a bit more complicated at SU3, where the Cartan subalgebra is actually not that simple anymore. And what we'll discover now is in fact a pretty similar picture. It wouldn't just be transitions up and down, they will be transitions left and right as well. But the basic picture is the same. We'll have a bunch of weights and a bunch of operators that move around between those weights. So, SU3. As I already noted, that is the full group of unitary transformations with determinant 1 in a three-dimensional complex space, and it has 8 generators. Those of you who do magnetic resonance will remember the 3 Zeeman operators and the 5 quadrupole operators, which together make 8. And those of you who did particle physics will remember the Gell-Mann matrices, which are the generators of SU3 and the generalization of Pauli matrices. I've listed them in the handout for you. You can take a look at them there. I will not transcribe them on the board. But what you should look at there is the fact that 2 of them, rather than 1, are now diagonal. In particular, we have lambda 3, which is 1 minus 1, 0, 0, 0, 0, and the rest of them, and lambda 8, 1 over root 3, 1, 1, minus 2. Yes, the NMR people can recognize axial quadrupole interaction, yeah? So these are both diagonal. For that reason they commute. You can multiply them in any order and the result will be the same. But these guys span the Cartan subalgebra. And the weights can now be either with respect to this operator or with respect to this operator. So any particular eigenvector will be the eigenvector of both, but with different eigenvalues. So 0 in this case and minus 2 in that case, for example. So for each eigenvector, we now have 2 weights. So weights became 2 vectors. What I'll take as eigenvectors, because these things are diagonal already, is the usual things. Just the Cartesian direction parts. And then take a look at what the eigenvalues are. And mu1 is a half root 3 over 6. It's the first pair of weights. Mu2 for the second vector there, minus a half root 3 over 6. And the third one, mu3, corresponding to that one, is 0 minus root 3 over 3, or 1 over root 3. I wouldn't touch on the normalization here, it's a bit unobvious. But what we now have is the set of 3 root vectors, and we can now plot them in a 2-dimensional plane. Whereas in the case of SU2, we only had one line, because the weights were scalars. What we now have is a plane. And this would be the eigenvalue with respect to H1, and this would be the eigenvalue with respect to H2. It's a conventional name, so H2 is this one, and H1 is this one. And what we get is this. The diagram here. And just as we had operators in SU2 that accomplish transitions between those weights, so we will have operators, I will not draw them out, but they exist, accomplishing transitions between these guys. And what I'll do is I'll just draw you right next to it a reminder from SU2. So this is SU3, and here's what we had for SU2. So see, we only had 2 weights, and we had operators that take us from one weight to the other. And because the weight was a scalar, they were just on a single line. In the case of SU3, the weight is a true vector, so we have a plane spanned by the 2 directions corresponding to the 2 generators of the Cartan subalgebra. And then if we plot these eigenvalues we get a two-dimensional plot, but, well, it has three weights on it, and there are transitions between those weights accomplished by some analog of a raising and lowering operator that happens to live in SU3. Okay, so that is the definition of a root and a weight. Well, not yet the definition of a root, that comes next, but the definition of a weight. And so when you read literature on particle physics, hopefully this will serve to remove, well, quite a lot of the entry barrier that is associated with it. Right, okay, so moving on to the roots. We spent a considerable amount of time already on something that is known as the adjoint representation. Yeah, that is the representation of an algebra using itself and acted upon by commutation. So in the adjoint rep, so add, for example, A is in fact a commutator with whatever it is that it is acting upon. So in the case of SU2, it's a three-dimensional representation because what we have is L, for example, X, Y, or Z, LZ, that could be acting on itself, and then it's 0. It could be acting on Lx. Well, let's say L plus here. We'll choose a slightly more convenient basis, getting a plus. Or it could be acting on L minus, and that will be getting us minus L minus. So you see the representation space is three-dimensional because it can be linear combinations of these three. Everything else is linearly dependent. And then what we have is the fact that these three operators are in fact eigenoperators of the operator in the Cartan subalgebra with eigenvalues of respectively 0, 1, and -1, and you can instantly recognize the three-dimensional irreducible representation of SU2 here. And these eigenvalues in the adjoint representation, so 0, 1, and -1, are known as roots. I wouldn't move any further into this. I will just note this definition, that the weights of the adjoint representation are known as roots. And we could make a similar construction for SU3 here, but really because we will not be using it anywhere in the subsequent course, and it's a fairly complicated exercise in its own right, I'll just skip it and send you to the particle physics literature if you're interested. Right, so much for the definitions corresponding to the weights and roots of various SUs. And what we'll now move on to is the ways of building up larger spin systems, descriptions of larger spin systems from these elementary algebras. Now, as you know from, well, the undergraduate quantum mechanics course, when we put two particles together, the wave function multiplies. Equivalently, when we put two particles together in a composite system, their state spaces are multiplied with a chronic product. And what I'll do is write now the multiplication table for the corresponding operator space. So if the two state spaces are crossed together, then pairs of operators in those spaces are similarly crossed together. And when we build up, for example, a two-spin system, we will get this kind of multiplication table almost necessary. E, the identity operator, technically speaking, does not belong to the algebra, to the V algebra, but does belong to the enveloping algebra and does belong to the operator space. Has to be there, Lx, Ly, Lz. So the four operators spanning the space of 2 by 2 Hermitian operators. Then identity for the other spin, Sx, Sy, and Sz. And here in the table we will have Kronecker products of that. So this will just be E, a 4 by 4 identity matrix. This will be E cross SZ, Sx. This will be E cross Sy, and so on. This, for example, will be Lz cross Sz, and all the other elements are filled in appropriately. And these are the things, some of you may recognize, which occur in the coupling Hamiltonian. Because if we have two spins interacting, for example, via J coupling or dipolar coupling, what we'll get after quantizing the corresponding operators into quantum mechanics is products of individual spin operators, and then when we take matrix representations of them, they will transform into Kronecker products. So the simple recipe for building up a composite spin system is to take your operators for the individual systems and cross them together. If these were 2 by 2 matrices, the results would be 4 by 4 matrices. If these were 3 by 3, for example, for spin 1, and these were 2 by 2, you'll get 6 by 6, and so on and so forth. So what this is eventually is just SU2 cross SU2 without the identity operator, because remember, identity operator, strictly speaking, isn't necessary in the Lie algebra. Shouldn't be there, as a matter of fact. But it does occur in the corresponding space of operators, if you consider it as a space. And, well, this is how it proceeds. If you add extra spins, you add extra algebras to this cross product. And, of course, what happens very quickly is the dimension of these matrices explodes. If we have 10 spins, then we'll have 2 to the 10 by 2 to the 10 matrices. That's 1,000 by 1,000. That's borderline treatable on modern computers, even if you're doing complicated things. But anything bigger than that is, well, you have to go into considerably harder Lie algebra in order to find a representation that is, on the one hand, small enough to squeeze into computer memory, but on the other hand, accurate enough to reproduce the dynamics that you're trying to capture. If you're interested in that stuff, just Google state space restriction, and you'll find a considerable amount of literature on trying to work with approximate representations of these product algebras and capture the necessary dynamics and ignore something that may be inconsequential on the scale of things that we are simulating. Right. What we move on now is the relationship that I already briefly mentioned at the beginning of the lecture between SU2 and SO3. SU2 versus SO3. Now, this is the cause of a huge amount of confusion in physics, textbooks, and so on spin and angular momentum. So I have to be crystal clear here that in the context of spin dynamics and magnetic resonance, these two have absolutely nothing in common. SO3 is 3D rotations in physical space. It's the same physical space that I'm rotating in at the moment. SU2 is a group of unitary transformations in the wave function space. In wave function space. Has nothing to do with physical space. This is just a space of abstract algebraic objects that we have defined for ourselves. Nothing to do with rotations. The coefficients are in general complex. And we could have picked up anything as the wave functions. It could have referred to any process in any physical system. Any two-level system with two energy levels will have its dynamics described by SU2. So it's a dynamical group of a two-level quantum system. And this is a group of three-dimensional rotations in physical space. Please don't confuse the two. Even though they share certain algebraic properties, and I will now note a relationship between the corresponding algebras. So the tragic fact of nature that generates all this confusion is that the algebra SU2 is in fact isomorphous to the algebra SO3. So you can have a one-to-one correspondence between the two mathematically, and that means that the generators of SU2 commute in the same way as generators of SO3. These would then be the angular momentum operators, and these would be the spin operators. The structure constants are the same. There's a huge amount of similarity as a result, but as I say, they're very different physically. Insofar as the relationship between the groups goes, it's not an isomorphism, it's what's known as a 2-to-1 map. SU2 is bigger, and if we are to establish some kind of algebraic correspondence between the two, very strictly speaking, to each pair of elements here, specific pair of elements, there corresponds one element here, a double cover. So SO3 is isomorphous to a factor group SU2 divided by SU2. But as I said, physically speaking, very different things, doing very different things on very different physical parameters of the system. So when I hear that spin is an intrinsic angular momentum, I cringe a little bit because it really isn't. Okay, final topic for today is the universal enveloping algebras. We already touched upon the fact that quadrupolar interactions are actually leaking outside SU2. And now we'll note, well, again, a bunch of definitions really, that creates a home for such situations. Right, so we all know that we are usually quite happy for a single spin with operators Lx, Ly, and Lz. But it so happens that there are interactions in nature which are quadratic with respect to these operators. Now, the problem with things like Lx squared is it really doesn't have any place to live inside SU2, because SU2 is spanned by these, and they're commutators, and of course their commutators are themselves. There is no operation inside the SU2 Lie algebra except linear combination and commutation. There is no such thing as a square. If you commute Lx with Lx, the commutator is 0. So, insofar as the Lie algebra goes, Lx squared has no place in it. But if we allow products rather than commutators, what we get is a plane algebra. It's no longer just a Lie algebra because we have allowed products. So we get an associative algebra. And it's called universal enveloping algebra. So the envelope of SU2 is obtained by allowing plane products inside SU2. And in that case, we can, of course, have then Lx squared. If we are looking at a 3×3 irreducible representation of this, Lx squared will be there, but Lx cubed would actually be 0. It's nilpotent. Same for Ly and Lz. Lz will actually loop on itself. So what will happen then is we'll acquire extra operators, so Ly squared, Lz squared, Lx Ly, and Lx Lz, and everything else will be their linear combination. But again, if you count, so that is for the 3×3 irrep. If we have, for example, a 4×4 irrep, there will be further operators here. But for a 3×3 irrep, a very interesting fact emerges. If you count these linearly independent generators, 1, 2, 3, 4, 5, 6, 7, 8, again, it's generated by 8 linearly independent generators. It's something 3×3. It actually is the envelope of SU2 under the exponential map generates SU3 in the case of the 3×3 irreducible representation. So here's the mechanism of this leakage. Here's why in the case of magnetic resonance we are not actually confined to SU2 for spin. Some things can be described by SU3. That is because physical interactions within our system demand that we take that algebra and actually work inside the envelope where those interactions live. But if we then look very carefully at what that envelope actually is, it turns out to be SUM with a slightly bigger n. Okay, I hope I haven't confused you completely with this. This is certainly a very difficult topic, and I hope I haven't made any drastic errors in trying to simplify it a little bit to make it accessible. Okay, from the next lecture we move into the advanced topics of magnetic resonance, such as relaxation theory, rotating frame approximations, secular approximations, and things like that.